Hello, my name is Maddie. I'm a fourth year student doing an honor specialization in chemistry, and today I'm going to be talking about gases and laws for your 1302 midterm. So there are three states of matter, solids, liquids, and gases. So in solids, the atoms are locked in position, and the strength of these interactions between the atoms determines the melting point of the compound. And so the stronger the interaction, the higher the melting point is going to be, so the harder it will be to break these interactions. These atoms possess vibrational energy, which increases with temperature, and when the vibrations overtake the attractive forces, it becomes a liquid. In liquids, the atoms are free to move around, but there's still some attraction which keeps them touching. And the substance takes the shape of the container. Each atom takes up more space than when it's in its solid form because of its increased motion. And the solid is usually denser than its liquid form. However, water is an exception for this rule. And at high enough temperature, the attractive forces are overcome, and this becomes a gas. And so atoms and gases have lots of freedom to move around, and they will also fill the container like liquids. And atoms and gases move with translational energy as well. So there are some assumptions of gas behavior that we follow. So one of the assumptions is that the pressure isn't too high, so this means that the atoms of gases have no volume. And we also assume that gas is well above condensation temperature, so there are no forces acting on these atoms. So we're going to talk about a couple of laws. The first one is going to be Boyle's law, which is P1V1 equals P2V2. And so this law states that for a constant temperature and number of moles, the volume and pressure of the gas are inversely proportional to each other. Another law is going to be Charles' law, which is V1 over T1 equals V2 over T2. And this law states that for a constant pressure and number of moles, the volume and the temperature in Kelvin of the gas are directly proportional to each other. So this is going to increase linearly or decrease linearly. And when we combine these laws together, we get the combined gas law. This states for a fixed number of moles, the equation is P1V1 over T1 equals P2V2 over T2. We also have Avogadro's law, which is V1 over N1 equals V2 over N2. And this law states that for the same temperature and pressure, equal volumes of different gases contain equal number of moles. So when we have a lower volume, we have less number of moles, and when we have a higher volume, we have a higher number of moles. So when we combine all of these laws together, we get the ideal gas law, which is PV equals nRT. And so in this equation, R is the ideal gas constant. And so this constant changes depending on what unit your volume and your pressure is in. So you just have to keep that in mind and make sure that you're using the right constant depending on what units you're working in. And also always remember that the unit for temperature is in Kelvin. So for the first practice question, you can pause it if you want to try it yourself, but I'm just going to go ahead and answer this. So we're going to use Charles' law because we're dealing with a constant pressure, so only the temperature and the volume are changing. So we're going to use V1 over T1 equals V2 over T2. And we are given that V1 equals 0.5 liters, T1 equals 291.15 K. So we are given that T1 is 18 degrees Celsius, but just like I said earlier, you're going to have to convert that into Kelvin. And then we have T2 equals 245.15 K. And we're looking for V2. That's our unknown here. So we're going to rearrange Charles' law for V2. So it's going to be V2 equals V1, T2 over T1. And then we'll just substitute our values in. Which gives us a final answer of 0.421 liters. So D is going to be our answer for that one. And then for this next problem, pause it if you want to try it yourself. But we're going to be using the ideal gas law for this one. So we're going to be using PV equals nRT. And so the question is asking if the pressure and the temperature are doubled, what's going to happen to the volume? So if we double the temperature and the pressure, the expression is going to become 2 of the original pressure times the volume, and then you're also going to have 2 of the original temperature there. So that's what your expression is going to become. So then we can simplify this to this, and you have a 2 on each side, so they're just going to cancel each other out like that, which is just going to make it PV equals nRT, meaning that your volume doesn't change because you end up with the same equation that you started with. So the answer is going to be E, the volume does not change. Okay, so moving on to talk about the molar volume of an ideal gas. So this just states that 1 mole of any ideal gas has the same volume at a given temperature and pressure. And so 1 mole of an ideal gas at 0 degrees Celsius in 1 atmosphere, this is called normal temperature and pressure. It's going to be 22.4 liters. So there are some variations of the ideal gas law. So we know that density is expressed as D equals mass over volume, and the mass is expressed as mass equals molar mass times moles. So when we combine these expressions with the ideal gas law, we get molar mass equals density, the R constant, and temperature over pressure. And so we also have Dalton's law of partial pressures, which is going to be pretty important. And so this law states that the total pressure exerted by a mixture of gases is the sum of all the partial pressures of these gases. So we have gas A, gas B, and gas C. And when you mix all of these gases together, the total pressure is just going to be all the different partial pressures added up together. So that's just what that equation states. So we also have mole fractions, which falls under this law. And so at constant temperature and volume, the pressure is directly proportional to the moles. And just keep in mind that the sum of all mole fractions is always going to add up to 1. So this is a good way to check if you calculated your mole fractions correctly. So Dalton's law of partial pressure also talks about the vapor-liquid equilibrium and vapor pressure, so like changing phases. And so vapor pressure is the partial pressure of a gas when equilibrium is reached. At this equilibrium, the rates of evaporation and condensation are equal. Vapor pressure depends only on temperature of the gas, and so at higher temperatures, the vapor pressure increases. And boiling point is the temperature when the vapor pressure of a liquid is equal to atmospheric pressure. So a lower boiling point is going to equal a higher vapor pressure. So this law also covers average molar mass of a mixture. And so this is the weighted average of the molar masses of the different gases in the mixture. So this is going to be the mole fraction times the molar mass of that one gas component. And so when you use this equation, you can find the molar mass average of the whole gas mixture. For gas reaction stoichiometry, this states that when pressure and temperature are constant, mole ratios are the same as volume ratios, and when volume and temperature are constant, mole ratios are the same as pressure ratios. And so there are some typical scenarios. So there's mole volume, which is the reaction is given in moles and the volume of gases are required. That's when you would use that. There's mass volume, and this could be used when the mass of one component is known and the volume of another must be found. There's volume, which is stoichiometric stoichiometric coefficients are proportional to volume, and pressure. So the stoichiometric coefficients are proportional to pressure. So for the kinetic molecular theory of gases, we have 5 assumptions. The first one is that the size of the molecules is negligible. The second point is molecules are point particles, so they only have translational energy, not vibrational or rotational. For the third point, collisions between molecules are elastic, meaning that the energy and the momentum are conserved. The fourth point is that there are no attractive or repulsive forces between these molecules that we have to account for. And the fifth point is that the average kinetic energy of molecules is proportional to the temperature in Kelvin. So we're just going to talk about this fifth point a little bit deeper. And so the kinetic energy is given by this equation where m equals mass and the u equals speed. So u squared is the mean square speed, which can be found by the average of the squares of the speeds of the molecules. So this equation here. And in this equation, the molar mass is going to use units of kilograms per mole, not grams per mole, which you're probably used to. And so the higher the temperature, the faster the molecules move, and the lower the mass of the lower mass molecules move faster as well. So for a Maxwell-Boltzmann distribution, this theory shows the distribution of molecular speeds. So on the left here, we see that molar mass affects speed. And then on the right here, we see that temperature, the effect that temperature has on speed. So for root mean square speed, this is the equation. And for two gases, A and B at the same temperature, you can use this equation. You don't need to account for the ideal gas constant or the temperature there. So effusion in Graham's law. Effusion is the flow of gas molecules at low pressures through pores or pinholes in a container. The rate of effusion of a gas is inversely proportional to the square root of its molar mass. And so lighter molecules effuse faster than heavier molecules. If two gases that have equal partial pressures effuse through a pore, we can use this equation here, where F is the enrichment factor. And so we just have one last question. If you want to pause it and try it yourself, I'm just going to start working on it. So for this, we need to use Dalton's law of partial pressure. And so we're given that the mixture has equal masses of N2 and NH3, and we're told that the total pressure of the mixture is 10 kilopascals. And so we're going to let the mass of each gas be M. And so the moles of N2, we're going to call that. That's how we're going to label it. And so it's going to be the mass over the molar mass of N2, which is going to be M over 28 grams per mole. And for the moles of NH3, we'll call this. That's how we'll label it. It's going to be mass over molar mass of NH3, which is going to be M over 17 grams per mole. And so the total moles is going to be that. So we can fill this in a little bit. Which will give us, you can take the M out of there, which is going to leave you with this expression. And so our N total that we were calculating up there is going to be this when we calculate that all out. And our mole fraction of NH3, we'll label it as that. It's going to be the moles of NH3 over the total moles. So I'm going to head to the next page to calculate this because I'm running out of room. So to calculate the mole fraction, we're just going to fill in this equation. That's a multiplication sign. So that's what we get when we follow that calculation through. And then we want to calculate the partial pressure of NH3. So we will label that as this. So this is going to be the mole fraction multiplied by the total pressure. And so we just calculated that the mole fraction is going to be 0.621. And we were told in the question that the total pressure is going to be 100 kilopascals. And so this is going to give us 62.1 kilopascals. And so if we look back at our answers, the one closest to our answer is D.
Okay, hi everyone. So my name is Kylie, and today I'm here with Josh, and we're going to be going over the thermochemistry section of the course. So this is going to cover the important parts of Chapter 2 in the workbook. All right, so starting off with 2.1, which covers heat, work, and energy. So here we're going to be looking at a little bit more conceptual stuff as opposed to calculations. And the first thing that you're going to want to understand is the three different types of systems. So we have open, closed, and isolated. So with an open system, you can see matter and heat can go in and out. So in this flask here, maybe some of this water can evaporate, so that's the matter. And then let's say it was cold water and you left it out, eventually would kind of warm up to room temperature, so that's our heat. The same thing would happen with a closed system, so we can have heat moving in and out, but you can see now we have a stopper at the top of the flask, so we can't have that evaporation of the water anymore. So matter cannot go in and out of a closed system. And then with an isolated system, neither matter or heat can go in and out. And so you can see here we have our stopper, and we also have the flask insulated so that its temperature stays more or less the same. Moving on to the next concept you'll want to understand is intensive and extensive properties. So these are easiest to remember if you think of examples. So intensive properties are the ones that are the same regardless of sample size. So temperature makes a lot of sense here because whether you have like a big pot of boiling water or just a little cup, the temperature is the same. It's still 100 degrees Celsius. Extensive properties, on the other hand, are dependent on like how much stuff you have. So mass is our example here because that big pot of water and the little cup are obviously going to register different rate values on a scale. Another important category is state functions. So these are properties that depend only on the final and initial state. So the value of the property is the same regardless of what kind of path was taken to get there. So now that you've gone through the entire thermochemistry unit in class, you might be confused about how this content up here relates to the rest of the stuff that you guys have learned. And so you'll see in the rest of the video that the properties of enthalpy, entropy, free energy, and internal energy are introduced. And so it's important to understand that all of these properties that were introduced to you in this course are extensive properties and they are state functions. And make sure you know this because this is a great thing that can come up in multiple choice questions. Okay, and then throughout the chapter, you're also introduced to the laws of thermodynamics, and there's 3 of them. And so instead of just kind of like listing them all out right now, I'm going to bring them up as they relate to the content because it's definitely more important to understand like their meaning and application more than just like memorizing them. But right now is where the first law comes in, which says that the total energy of an isolated system is conserved. So the significance of this is that it gives us this formula, which basically says that the heat, or Q, that is gained in a given scenario is equal to the heat that is lost, just one is positive, one is negative. And so that's what we mean when we say that the energy is conserved. And then this is the formula for Q, and we'll see how to apply that in the next practice question. All right, so we have a question here, which is 50 grams of ice at 0 degrees Celsius, when placed in water, can cool a maximum of how many milliliters of water from 20 degrees Celsius to 0 degrees Celsius? And then we have some values here. Okay, so let's work through this. First, let's kind of think about it. So we've got, an ice cube, and then we kind of have some cup of water here. And so basically, when they come into contact, the ice is essentially going to cool the water because ice is colder than water. And then it's a little bit backwards to think about, but the water is kind of like warming the ice because it's causing it to melt. So we can set up our formula here of Q gained equals negative Q lost. And so we're going to say that our ice, which is the one that I said was kind of being warmed, is our Q gained, and then our water is going to be our Q lost. And so we actually saw that when that ice is getting warmed and it's getting melted, they already gave us a value for that. So it's going to be 6.01 kilojoules per mole. And then we saw that we had 50 grams of ice. So we're just going to want to also convert that to moles. So we do that by taking our mass and dividing by the molar mass of ice or water, H2O, which is 18. Okay, and then on the other side for the water, you've noticed that we don't have one of these values. So this is where we're going to have to use our Q formula here. So we have negative sign and then MC delta T. And let's actually fill in those values now. So mass of water is what we're trying to calculate. We know that the C of water, the specific heat capacity, is 4.184. And then our change in temperature, so we're going from 20 degrees Celsius to 0 degrees Celsius, so final temperature minus initial temperature will be like that. Okay, so then for this part of the calculation, we just want to make sure we are going to multiply this by 1,000 to convert to joules, just because we see that we have joules on this side. So let's just do that really quickly. So that's going to be okay. So on this side we have 16,694 joules. And then if we just rearrange and solve for M here, so we'll have M equals 16,694 joules divided by 4.184 joules times, and I'm just going to put 20 here. So we can keep it as 20 degrees Celsius. And so these negative, like this will be negative 20, but that will cancel out with this negative sign to give a positive. So that's why I don't have any negatives in my final calculation here. And so as a mass, we get 199.5 grams, and then we know that the density of water is 1 gram per milliliter. So with water, if we have 199.5 grams, we also have 199.5 milliliters. That is pretty close, rounds up to 200. So our answer is D.
Today, I'll be introducing the enthalpy chapter as a part of your thermochemistry unit in 1302. Let's just get started. Internal energy, as you learned in the last section, is the total energy of a system, where it's represented by the variable E, and it is equal to heat plus work, whereas enthalpy, represented by the variable H, is equal to the internal energy of the system plus pressure times volume. And now, like internal energy, we can't actually measure the total enthalpy in a system, and so we have to measure the total change in enthalpy, which is represented by this equation at the bottom, where it just has a bunch of deltas in front of things that might change in a certain reaction. The main point I want to stress about this slide is on the right, and it's that delta H is equal to heat via this math over here. And that's how you're going to be calculating a lot of your enthalpy changes in certain questions. And again, another note, if pressure is constant, then the total change in enthalpy is only concerned with heat. Most problems will be like this unless otherwise stated. Now moving on, physical processes and latent heat, where latent heat is associated with energy in phase changes. So if we look at this chart on the right, and if I use just this top column as an example, or top row, sorry, where we melt ice, so water is a solid into a liquid, it's plus 6.01 kilojoules per mole of heat. Now, that makes sense because obviously we have to add heat to the water or to the solid to melt it into a liquid. If we take the reverse process, we are taking away heat from that liquid to freeze it, and so it's going to be represented as a negative. I really want to stress that you guys all watch your signs when you're doing these kinds of questions to make sure that everything kind of makes sense with certain phase changes that might be occurring in a certain reaction or question. And I want you to think about, again, the kind of energy or absence of energy that is needed for a phase change. Now, just a quick note on standard conditions, where it's denoted by 1 atmosphere or 101.33 kilopascals, and 25 degrees Celsius or 298.15 Kelvin. I just want you guys to know that these are always going to be standard conditions. If you guys ever have any questions where they give you pressure in a different kind of measurement, always make sure that all of your units that you use throughout the question are the same. So if you're given, an atmosphere, you have to convert it to a kilopascal if there is a variable within your equation or in your question that is also in kilopascals. Never do a question without converting units. And just as a quick note, the triangle or delta denotes a change in the system. H is represented as enthalpy, and this little circle here indicates that the system is under standard conditions or under these conditions over here. Now, unless otherwise stated, most tables will be given in standard conditions, and if they're not, don't freak out. They will give you the units or a clue on how to find them. Generally, you're going to be seeing this equation a lot. So delta H of a reaction is equal to the sum of the enthalpy of products minus the sum of enthalpy of reactants, where we see an example down here where ethane gas is turned into ethylene gas plus hydrogen gas, where the result is a negative enthalpy value, where it's represented by negative 137 kilojoules per mole, Obviously, it's negative because we're breaking bonds, and in this case, we're releasing energy from the system. So this reaction is exothermic. However, if we look at the reverse process where we form ethylene gas and we add hydrogen gas to it, we form ethane gas. Since this reaction is exactly the same but just in reverse, we require the same amount of enthalpy but just with the opposite sign. Here it's a plus because we have to add energy to form new bonds, and in this case this reaction would be endothermic. Now you might be wondering how we kind of measure enthalpy, and we established earlier that the total change in enthalpy is equal to heat, and so we can say that the study of heat flow is called calorimetry. I'm sure you guys have seen this a lot. I know I have a simple styrofoam cup calorimeter. In your case, will essentially be considered an isolated system where we can study the enthalpy via this calorimeter. Just to note, the styrofoam calorimeters are only for liquid reactions. You'll see a lot of these questions like this with simple calorimeters. And in order to kind of calculate what you need to calculate in these kinds of questions, you can generally use a formula that I'll introduce later. But first, let's consider this reaction here, where hydrochloride plus sodium hydroxide is equal to, or turns into water and sodium chloride. This process is exothermic. And since we can kind of consider the styrofoam cup and everything inside it as an isolated system and everything outside is our surroundings, the math essentially boils down to this bottom equation over here. We can drop the heat of the surroundings and heat of the system, since all of the heat of the reaction will be contained within the calorimeter. Generally, this is your formula here. You used it in a previous chapter, where the Q of the solution is equal to the mass of the solution times the heat capacity of a solution times the total change in temperature of the solution. Again, if the reaction is performed under standard conditions, we can say that the heat of the reaction is equal to the total enthalpy change under standard conditions. Now, there are two ways of calibrating a calorimeter. In certain questions, you will have to do this. The first is adding a known amount of water, where the math is displayed here, to simplify to an equation where you can directly calculate the heat capacity of a calorimeter. If a known amount of hot water is added to the calorimeter, you can then measure the heat capacity of the calorimeter once the system has come to thermal equilibrium. The second way you can do it is you can carry out a chemical reaction, a liquid chemical reaction with a known heat of said reaction. Therefore, you can get the total change in temperature and then the total heat of said reaction. Here I display a example where the question says 150 grams of water at 40 degrees Celsius were added to a calorimeter at 25.5 Celsius. The final temperature of the calorimeter and the water was at 30.2 Celsius. What was the heat capacity in joules per Celsius of the calorimeter? Now, using that first method, we're adding a known amount of hot water to our reaction. So we can use this formula here and essentially just plug in all of our values to obtain our answer of 1308.6 joules per Celsius. Again, notice how we kind of used the same temperatures finals, or as our final temperature. Now moving on to the standard enthalpy of formation. Standard enthalpy of formation is also known as the standard heat of formation. Essentially, it is the enthalpy change for a reaction where 1 mole of a substance is formed under standard conditions from its reactants. The state of a substance under standard conditions is also called a standard state, and the reference state is the state of said element it would be most stable in. So here is a chart of certain elements in the reference states. Hydrogen, for example, if we were to add energy or take away energy, or sorry, enthalpy from hydrogen to transform it whether into a liquid or a gas, and it is under standard conditions, then there would be a value for that. But if you ever find hydrogen gas or carbon graphite solid or nitrogen gas or any of these other examples in their reference states, within that question, the enthalpy change for specifically that element will be 0. And again, just a quick note, some elements can exist in different forms. These forms are called allotropes, where carbon can also exist as graphene, graphite, diamond, and fullerene. Again, here are some examples just written above. Again, notice that the delta H subscript has changed to show an F now, representing formation. And again, to stress my point, bromine gas here is not in its reference state because it should be a liquid. Since it's in a gas, it is now plus 30.9 kilojoules per mole, even though it is bromine too. It is in a different state. Here I picture an example question. You can pause the video here to do it yourself. Where the question states, determine the standard enthalpy for the following reaction using the standard enthalpies of formation found in the reference data sheet. Here again, you kind of see this equation where the total change in enthalpy under standard conditions for this reaction is the sum total of the change in enthalpy of formation of products minus the reactants. The second step you would probably do is just balance out this equation just to know what you're dealing with, and then you would refer to your chart to grab these values. Again, I stress that hydrogen gas is now in its elemental state, so it's going to have a value of 0, and then all the other values follow. The next thing, or the final thing you would do is just plug all of these values into the equation. So we know out of our products, which it's methanol and water. For methanol, it's negative 238.7, and for water, it's negative 285.8 kilojoules per mole. I slot them both into this part of the equation, and then you subtract from your reactants. Notice how I have now plugged in 0 for hydrogen gas, but I have highlighted, or I have put the molar coefficient that was in front of the hydrogen. If any of these reactants had molar coefficients in front of them, you would add this to your equation to get the correct answer. And we see that the answer turns out to be negative 131 kilojoules per mole, which is representative of B. Now moving on to Hess's law, I'm sure we've seen this a bunch of times, I know I have. And as a reminder, enthalpy is a state function, which means we can find the total change in enthalpy under standard conditions if we know the other two reaction enthalpies. Generally, again, we see this formula again, and we would slot all of our values just in this order. Again, don't forget the molar coefficients when you're inputting the values into the equation. For bond enthalpy, total bond enthalpy, and average bond enthalpy is the energy required to break 1 mole of a specific type of bond, whether that be a single, double, or triple. You have to be very mindful of this because it can change your answer. Again, this is only for gaseous phase chemicals. So if we see here on the right, if we want to break hydrochloric acid or hydrochloric gas, it turns into hydrogen gas and chlorine gas. It is plus 431 kilojoules per mole. And in total bond enthalpy, it's the same, except you break all of the bonds in a compound or a gaseous compound. So this example over here shows methane gas being broken into carbon and 4 hydrogens, and it is plus 1656 kilojoules per mole. Now, if we were to take the same reaction shown in total bond enthalpy and divide it by the value we receive at the end by 4, because we would be breaking 4 bonds, we would then have the average bond enthalpy. Here are the 2 methods listed to calculate the total bond enthalpy. And now we have another example question, where it states that estimate the enthalpy of formation, the delta HF standard conditions of hydrogen peroxide for the relevant bond enthalpy data, from the relevant bond enthalpy data provided. Now notice it's very important to note the structure of how these are actually drawn. Hydrogen only has a single bond in between them, oxygen has a double bond in between them, and hydrogen peroxide has a single bond in between the H and the O, and a single bond in between the O and the O. When we write out this formula, it is bonds broken subtracted by the bonds formed. I'm pulling 498 and 436 from the double bond that we would be breaking from the oxygen, and the single bond we would be breaking from the hydrogen. So it's 498 and 436 subtracted by 138. So the bond that we would form between the oxygens, which is 138, and then the bonds we would form between the oxygen and the hydrogen, which would be listed as 464. But since we're breaking two of them, we have to kind of put that in our equation. And then we receive the answer of negative 132 kilojoules per mole, which would correspond to the answer A. And just a quick few notes about the total change in enthalpy of gas phase reactions. We utilize the same equation, and the total bond and the and here, just moving on to a couple quick notes about the total enthalpy change of gas phase reactions. You essentially utilize the exact same equation as I used in the example. This is just fleshing out a few more details. And again, if there is any other chemical that is in another state that's not a gas, the bond enthalpy of that reactant or product is not included, or you can just write 0 in your answer.
All right, so moving to 2.3, we introduce a new property here, which is called entropy, and our symbol for that is delta S. So entropy sounds really similar to enthalpy, but it's actually totally different. It's a little bit of an abstract concept, but I really think the key to understanding it is to think of it as a synonym for disorder. So if something has high entropy, it's very disordered and chaotic. And if something has a low entropy, then it's very neat and ordered. So as an example, a solid has the lowest entropy, then a liquid, and then gas has the highest entropy. And that's just because of the way that the particles are arranged, which you can see in the picture here. And then with gases specifically, when you have more moles of gas, it is the same thing as having more disorder, so higher entropy. But we'll talk about this a bit more when I do the practice question in a few moments. Okay, and so remember those laws of thermodynamics that I talked about? Well, the second and third ones are actually all about entropy. So let's start with the second one, which says that every spontaneous process increases the entropy of the universe. So what this is saying is that the universe will favor processes where the entropy increases. So if you think about this mathematically, it means that the final entropy will be greater than the initial entropy. So the universe favors delta S values that are positive or greater than 0. Again, this is pretty abstract. So the best analogy is to think of your bedroom. So how many times have you not even been trying for your room to get messy, and it just does because you're rushing around to get ready for class or whatever. But does your room ever just spontaneously become clean and neat? No, the universe doesn't favor that. You'd actually have to put in extra effort and energy if you wanted that to happen. So just like your bedroom, the universe always favors going more towards disorder or a positive entropy. All right, so now that we have the conceptual understanding of entropy, we are going to bring in a calculation, standard entropy change. But the good thing is that this calculation is actually exactly the same as the enthalpy one that Josh introduced, but instead of using enthalpy of formation values, you'll be using standard entropy values, which would be given to you in a different table. And just a little helpful fact is that these standard entropy values are actually calculated based off the third law of thermodynamics, which says that a perfect crystal has 0 entropy at a temperature of 0 K. So you don't really need to memorize all the details of that, but I really just wanted to make sure that I was kind of checking off all the boxes in terms of going through the significance of all 3 laws of thermodynamics. But anyways, back to the calculation. It's exactly the same as the standard enthalpy of formation one. So you're doing the sum of the products minus the sum of the reactants. Just remember to multiply by your stoichiometric coefficients if necessary. And also just keep in mind that the units for entropy are different from enthalpy. So enthalpy we saw was kilojoules per mole, but entropy values are usually in joules, and they also have this temperature aspect in there as well. Okay, so let's do an entropy practice question here. So this one says, which one of the following reactions will have delta S of the system greater than 0? So remember that if the change in entropy is greater than 0, then that means that the final entropy should be greater than the initial entropy, because when you do the difference between them, it should be a positive number. And so remember that a higher entropy means more disordered, and then the lower entropy will mean more ordered. So let's go through each of these scenarios and see if any of them or which one of them fits that. So starting with A, we see that we have liquid, gas, and then on this side we have liquid and gas. So our states are kind of the same, but if we just look at the gas specifically, here we have 8 moles of gas, and here we have 5 moles of gas. And so remember I said the more moles of gas you have, the more disordered the situation is. So here we have an initial situation that's more disordered than our final situation. That's the opposite of what we want. So we can eliminate A. Looking at the next one, again, everything's all gas, so let's count our numbers. So we have 2 moles of gas plus 1 mole, that's 3 on this side, and just 2 on this side. So again, we have an initial situation that's more disordered than our final situation, so that also will not be our answer. Looking at this one, we don't have any gas, so we're not counting moles, but instead we're looking at the situation as a whole. So here we've got some ions dissolved in solution, so basically liquid, and then we've got a solid. The solid is more ordered than having like a bunch of ions disassociated in a solution. So again, this is the opposite of what we want because our final is more ordered than our initial, so not C. In D, we start with a liquid and then it becomes a gas. Gas is more disordered than liquid, so our final state is more disordered than our initial. That is what we want. So it's looking like D is our answer, but let's just check the last one. So again, we're all gas here, so we're going to be counting the number of moles. And we've got 1 mole here, 1 mole here, 3 moles here, and then just 2 on this side. So our final state is more ordered with 2 moles than our initial state, which has 4 moles. So again, that's not what we were looking for. So that confirms that D is our answer. So questions that have to do with entropy, and they're asking you if it's a positive or a negative entropy, you want to look at first the different states that you have, but if everything's kind of equivalent there, then you can start looking at the number of moles of gas and counting those up. Okay, so finally we're going to move on to our last lesson and property, which is free energy. It's also called Gibbs free energy, so that's where our symbol of delta G comes from. And so basically this guy is kind of like a combo between enthalpy and entropy. So the formula for it, you can see, depends on both because we've got delta H in there and we've also got delta S. And so when we're looking at whether a process is spontaneous, basically whether it can happen without the help of additional energy, delta G really is the king here. So it really has the final say on whether a reaction is spontaneous or not. So make sure you know these rules here. So when delta G is negative, the reaction is spontaneous. And then when delta G is positive, the reaction is non-spontaneous. And a special case is when delta G is equal to 0. And this happens with phase changes, so like melting or boiling or freezing. And then once you've got that kind of internalized, the next thing that you're going to want to tackle is this chart here. So this basically just goes through all the scenarios of like delta H and delta S being positive or negative, what kind of effect that has on delta G, and then the spontaneity of the reaction. And so yes, you can memorize this, but it's also all like based on this equation here. So you can try out the different signs and see that like it mathematically makes sense. So for example, if we looked at the first scenario up here, we have delta G, and so we'll have a negative value for delta H, and then a positive value for delta S. And so when you multiply this and this, that's going to give a negative value. So you're essentially doing a negative value minus another negative value. So obviously that's going to make delta G negative. And so you can see that as you go through the different scenarios. Just with these two bottom ones, it will depend on the temperature, whether it ends up being spontaneous or not. All right, and then finally we have one more equation and calculation, which is calculating standard free energy change. But guess what? This is exactly the same as the formula that you saw for enthalpy and entropy. So same idea, these standard free energy values would be given to you. You would sum them up, just make sure you're multiplying by your coefficients, and it follows the exact same format as your other calculations. So we will end off with a practice question related to free energy. So this one says, estimate the boiling point in Kelvin of methanol. And they give us data for methanol as a liquid and then methanol as a gas. And we have our enthalpy and our entropy. So the really key thing that you want to remember for this question is that at phase changes, so this is a phase change because we're seeing boiling. At phase change, delta G is equal to 0. So we can take our formula, delta G equals delta H minus T delta S, and we can set this side to 0, and then we're going to calculate our delta H. So we're going from CH3OH liquid to CH3OH gas. So this is our initial, and then this is our final. So for delta H, the change in enthalpy, we're going to do our final minus our initial. So we'll do negative 201.2 kilojoules per mole minus negative 238.6, and I'm actually just going to move this just so there's a little bit more room here. Okay, and then minus T. So T is what we're trying to solve for. We're trying to find the temperature at the phase change when delta G is equal to 0. And delta S, we're going to do the final minus the initial. So we'll do our gas value of 238 joules per mole per Kelvin minus 127. And I don't have room for my units there, but we'll just leave it like that. It's the same units. So let's calculate this. So this is going to be 37.4 kilojoules per mole minus T times 111 joules mole. Okay, and then this is the thing I was talking about before. Enthalpy and entropy have different units. So we're going to want to make sure that we convert, make them equivalent. So I think it's just easier to convert this to joules by multiplying by 1,000. So we'll get and I'm just going to move this up. And so just rearranging for T, I'm going to move this over to the other side. Sorry, this should be joules here. And I'll just switch my color so you can see it on the purple here, but T is going to be equal to 37,400 joules all over 111. Again, I just got rid of we have negatives on both sides, so they just cancel out. And then the joules per mole units will cancel out. We're left with 1 over Kelvin to the -1, which is just Kelvin, so that'll give us our temperature answer. So this gives us 336.9. It's pretty close to 337, which is D. So that's our answer.
Hey guys, so I'm going to take you through 2 important areas that highlight the fundamental aspects of chemical reactivity, the equilibrium constant and the solubility of ionic compounds. These concepts are central to understanding how chemical reactions behave in solution and how various factors influence the formation of precipitates. Let's start with the equilibrium constant, which is often represented as K, for any reversible chemical reaction such as the one shown here. The equilibrium constant expression is then defined as this. This expression is dimensionless and provides a snapshot of the ratio of the concentrations of products to reactants when the system is at equilibrium. A few important points about K are that if K is greater than 1, the reaction favors the formation of products, meaning that at equilibrium, the concentration of products exceeds that of the reactants. Conversely, if K is less than 1, the reaction favors the reactants, and very little product is going to be present at equilibrium. Considering the reversibility is also important. So reversing a reaction inverts the equilibrium constant. That is, if the forward reaction has a constant K, the reverse reaction will have a constant of 1 over K. And when adding equilibrium reactions together to get a new overall reaction, the equilibrium constant K for the combined reaction is calculated by multiplying the equilibrium constants of individual reactions that were added together. So essentially, K overall is going to be equal to K1 times K2, where K1 and K2 are the equilibrium constants of individual reactions. Another important concept linked to the equilibrium constant is a reaction quotient, which is Q. Q is calculated just like K, but with the current concentrations of reactants and products, regardless of whether the system is at equilibrium. And the equation for it can be seen here. And it can be also considered for pressure, in which the equation can be seen there. By comparing Q and K, we can also predict the direction of the reaction. If Q is less than K, the reaction will proceed forward to produce more products until equilibrium is reached. If Q is greater than K, the reaction will shift in the reverse direction to form more reactants. And if Q is equal to K, the system is at equilibrium and there is no net change in the concentration. Furthermore, changes in temperature, pressure, and concentration can disturb a system at equilibrium. And according to Le Chatelier's principle, the system will adjust to partially counteract the change and reestablish equilibrium. So, for example, increasing the concentration of the reactants will typically drive the reaction towards the products. These principles not only explain the distribution of species at equilibrium, but also tie into thermodynamics. The free energy change, or delta G, for the reaction is related to K, where a negative delta G indicates spontaneous reaction, delta G being equal to 0 means the system is at equilibrium, and a positive delta G implies a non-spontaneous reaction, all under standard conditions. So, in the following example, we are going to try and determine which of the following actions will cause the reaction to shift to the right, which would produce more ammonia. So, if we look at action 1, which is adding H2 gas, when you add more of a reactant to a system, it will try to use up the extra reactant by shifting the equilibrium towards the products. So, adding hydrogen gas will shift the equilibrium to the right, favoring the formation of more ammonia. Then, if we look at the action of decreasing the volume of the container at constant temperature, decreasing the volume increases the pressure of the system. And if we remember Le Chatelier's principle and we apply it, the reaction will shift to the side with fewer moles of gas to relieve pressure. So we can count the moles of gas on each side, where in the reactant side, there is 1 plus 3, totaling to 4 moles of gas. And on the product side, there's 2 moles of gas. Because 2 is less than 4, the equilibrium will shift to the side with 2 moles of gas, which is the product side. Therefore, decreasing the volume shifts the reaction to the right. Finally, if we look at increasing the temperature, the reaction has a negative enthalpy change, which is negative 92.6 kilojoules per mole, which means it is exothermic. In an exothermic reaction, heat can be treated as a product. So, increasing temperature adds heat to the system. So the reaction will shift in the direction that consumes the heat. In other words, the endothermic direction, the reverse reaction. And this causes equilibrium to shift to the left, so not the right. So if we put this information all together, we can see that action 1 shifts the equilibrium to the right, action 2 also shifts it to the right, and action 3 shifts it to the left. So it is only answers 1 and 2, and so the answer is B. Now let's shift our focus to solubility of ionic compounds, a topic equally important in understanding how reactions in aqueous solutions. So, solubility refers to the amount of substance that can dissolve in a given volume of solvent at a specific temperature. Ionic compounds exhibit varying solubilities, and we typically classify them into 3 categories. Soluble compounds, which dissolve readily in water. Some examples are like nitrates, acetates, and salts containing alkyl metal ions, which are generally soluble, and slightly soluble compounds. So some salts dissolve only to a limited extent. So an example might be calcium sulfate or silver chloride, which fall into this category. So their solubility is enough to be measurable, but it's not enough to be considered fully soluble. And insoluble compounds. These compounds that dissolve very little in water, so typically less than 0.1 grams per liter at room temperature. Common examples include barium sulfate and calcium carbonate. Generally, carbonates, phosphates, and hydroxides are insoluble unless they're paired with an alkyl metal ion or ammonium. The solubility product constant, so Ksp, is an equilibrium constant that measures the extent to which an ionic compound dissolves in water, essentially indicating how much of a solid substance can be dissolved in a solution at a given temperature. At a higher Ksp value means a greater solubility of a compound in water. The solubility product constant, so Ksp, primarily depends on temperature, meaning that while other factors like the presence of common ions can influence the solubility, the most significant factor affecting Ksp is the temperature of the solution. An important aspect when dealing with solubility equilibria is the reaction quotient, which is Q. Q is calculated in the same way as Ksp, but using the current concentrations of the ions. So some relationships are that if Q is less than Ksp, the solution is unsaturated, meaning no precipitation occurs. If Q is equal to Ksp, the solution is exactly saturated and at the equilibrium. And if Q is greater than Ksp, the solution is supersaturated, and a precipitation will occur to reestablish the equilibrium. These concepts have practical applications. So, for example, when mixing two aqueous ionic solutions, understanding the Ksp helps to predict whether the precipitate will form. Key consideration in areas like that can be used for quantitative analysis. So, before we dive into a specific example using silver chloride, we're going to just briefly discuss ICE tables, which stands for Initial Change in Equilibrium. An ICE table helps to organize concentration data for species involved in an equilibrium reaction. So initial is the starting concentrations or amount before the reaction proceeds. Change is the change in concentration of the system as it moves towards equilibrium. And equilibrium is the final concentration at equilibrium. So if we look at silver chloride, we can assume that the solid initially does not contribute any dissolved ions. So the ion's initial concentration is often set to 0, which you can see here, if there are no other sources of these ions present. So as the solid dissolves, the ions increase in the concentration by some amount, which we're going to consider as X. So when we then express the final equilibrium concentrations, we're going to express them in terms of X. So let's apply the ICE table to silver chloride. And the dissolution equation is written as this. So suppose the solubility of silver chloride at 25 degrees Celsius is experimentally found to be 1.33 times 10 to the negative 5 moles. So this means that Ag plus and Cl minus both reach 1.33 times 10 to the negative 5 moles at equilibrium. So when setting up the ICE table, it is also important to remember that if a reactant is consumed, its change is written as negative X. And if a product is formed, it is written as positive X. And so, just as also a note, if you ever calculate X and find a negative value, it means your assumed direction of the reaction, or the way that you set up the changes, is opposite to what it is actually occurring. So in most cases, especially for dissolution problems, you expect X to be positive because it represents the amount that dissolves. So we can then work through the problem, and here X represents the molar solubility of silver chloride experimentally, which X is equal to 1.33 times 10 to the negative 5 moles. So therefore, silver and chloride, so Ag plus and Cl minus, both have values of 1.33 times 10 to the negative 5. So we can multiply them to get X squared. And when we input those values, we get a Ksp equal to 1.77 times 10 to the negative 10. So we can see that AgCl, or silver chloride, has a relatively small Ksp, confirming that it is only slightly soluble in water. So bring it all together. In summary, today we talked about exploring two key topics, one being the equilibrium constant, where we discussed its role in quantifying the relationship of concentrations of products and reactants at equilibrium, and we highlighted the significance of K and how the reaction quotient Q predicts the reaction's direction, and the role of the Chatelier's principle in adjusting to changes in a system. And then we also discussed concepts of solubility of ionic compounds, and we reviewed the solubility categories and the concept of solubility product, which is Ksp, and how the reaction quotient Q informs us about precipitation events. These ideas are critical for understanding how ionic compounds behave in solution and for predicting the outcome of mixing various ionic species.
Hi guys, my name's Heather, and I'm going to be talking about weak acids and bases in this section. So just to start with the definition, a weak acid or a base means that it does not fully ionize in solution, or in other words, the reaction doesn't go to completion and an equilibrium exists. So both the complex and the ions are existing at the same time. So we can see that here with the weak acid, we have both the ions and the complexes. Here are the complexes and the ions existing at the same time, whereas a strong acid completely ionizes in solution and the reaction goes to completion. So we can write that out as reactants existing in an equilibrium with products. And this is our equilibrium arrows just showing that both are existing at the same time. So there's a few different theories regarding the definition of acids and bases. The first being the Arrhenius theory, which states that acids produce H3O plus in water and bases produce OH minus in water. The next theory is the Bronsted-Lowry theory, which states that acids are proton donors and bases are proton acceptors. This is a better theory for weak acids and bases and is a little bit more general. But the best theory that we have specifically for weak acids and bases is the Lewis theory, which states that acids accept electrons to form a new bond and bases donate a pair of electrons to form a new bond. So here we can see the base acid adduct forming, where the arrow is showing the direction of the electron movement. If you need to, you can even draw out each species' Lewis structures to help you figure out the movement of electrons. Okay, so to give a little more meaning to acid-base reactions, we can talk about equilibrium constants. So just a reminder that if the equilibrium constant is less than 1, the reactant side or the left side is favored. And this is the case for weak acids and bases. Their equilibrium constants are actually much less than 1, which makes sense when we said the definition of a weak acid or base means that it doesn't fully ionize. And just remember that the larger the constant, the greater the ionization, or the more the reaction is favored to the product side. We are talking about equilibrium constants that are in like the 10 to the -4 or -5. So it's a lot easier to use a logarithmic scale and express their values as pKa for acids or pKb for bases. And the larger the pKa, the weaker the acid, and the smaller the pKa, the stronger the acid. Again, the terms strong and weak here are relative. We're still talking about weak acids and bases, not strong acids and bases. So the pH gets a little bit more complex since only some of what's dissolved will form H plus or H3O plus or OH minus. But we'll do an example soon so you can go through the steps and the assumptions that we can make. Okay, so percent ionization can be determined kind of depending on what information you're given. You can use an ICE table with pH or initial concentration of the solution, or using this equation here where alpha is the percent ionization, X is the concentration of the products, and C is the initial concentration. And just keep in mind if you're talking about acids and bases, and you can use these equations that were listed here to convert between pH or pOH if you need to. So there is an effect on the percent ionization and the pH if the solution is diluted, which should intuitively make sense. Like the more concentrated the solution initially is, the smaller the percent ionization and the further from neutral the solution will be. So remember that percent ionization is the amount of weak acid or base that's disassociated as a percent of the original concentration. So changing the original concentration or the denominator of this equation will change the percent ionization. So next, conjugate species are basically the connection or like the relationship between the reactants and the products. So the acids pair will be its conjugate base, which will act like a weak base in solution. And it's the opposite for the base. Its pair is the conjugate acid. So the acid and the conjugate base, or the base and the conjugate acid, will always be on opposite sides of our equilibrium. So one key relationship for acid-base pairs is that the Ka times the Kb always equals Kw, which is a constant. So this means that the stronger the weak acid is, the weaker its conjugate base will be, which again intuitively makes sense, especially looking at this equation written out. The common ion effect for weak acids and bases is really just the Chatelier's principle, showing that increasing the source of H3O plus will tip the equilibrium. In your workbook, example 3.3.7 is really good and will walk you through the calculation. I'm not going to go into too much detail on polyprotic weak acids, since again, there's a really good example in the workbook. It's example 3.3.8, but polyprotic basically means that there's more than one hydrogen that can be ionized in solution, and this occurs stepwise. So all subsequent steps must take into account the previous equilibrium. Okay, so next I'll go through a practice problem. If you want to pause the video and go through it yourself now before I share the answer, you can do that now. Okay, so to calculate the percent ionization, we'll need to determine the equilibrium concentration of H3O plus, and we can set up our ice table for that. So we're given that the initial concentration is 1.5 molar, and since this is the initial, we have nothing here. The change is we're going to be subtracting x, and then we're adding x here, adding x here. So then at equilibrium, we have 1.5 molar minus x, and we just have plus x and plus x. So now we can find the value of x by using our equilibrium concentration equation. So we know that Ka equals the concentration of H3O plus times the concentration of NO2 minus all over the concentration of HNO2. And in the question we were given Ka, so we can sub that in, 5.6 times 10 to the negative 4. And then we can sub in our x's here. So H3O plus and NO2 become x squared all over 1.5 molar minus x. And we're going to use the assumption that x is much smaller than 1.5 molar. So our equation then becomes x squared over 1.5. So just to clean this up a little bit, I'll rewrite it down here. Our Ka equals x squared over 1.5. And then we learn that x, which is the concentration of H3O plus, equals 0.029 molar. So now what we know what the equilibrium concentration of H3O plus is, we can calculate the percent ionization. So percent ionization equals concentration of H3O plus at equilibrium over the initial concentration of our acid, which is HNO2, initial down here, times 100%. So that gets us to 0.029 molar over 1.5 molar, times 100%, which equals to 1.9% ionization. So here we can see that C is the exact answer. So one of the main assumptions I made here is that that C minus X, so the initial concentration minus X, is approximately equal to just C. This is because it's less than 5%. The better way to test for this assumption is to calculate it, but if you know what X is, just use it. Yeah. So this next question here is asking for the pH. So again, you can go ahead and pause the video and practice before. Okay, so here this question is asking what the pH of a 0.15 molar solution of benzoic acid is, and our Ka is given. So again, you can set up an ice table here. I'll write out the reaction, C6H5COOH in water exists in equilibrium with H3O plus and C6H5CO, OO minus. So initially it's given that we have 0.1 molar. We're going to lose X, and then we're going to gain X over here. And these initial concentrations are 0, sorry. So then at equilibrium, we have 0.15 minus X plus X and plus X. Again, so we're given the Ka, so we know that Ka equals H3O plus times C6 H5COO minus all over C, the concentration of C6H5COH. And we know that Ka is 6.4 times 10 to the negative 5. And we know that, or subbing in our equilibrium concentrations here, we have x times x, or x squared, over 0.15 minus x. And again, we're going to use that assumption that 0.15 minus x is approximately equal to 0.15. So plug and play, we know that x is equal to the concentration of H3O plus, which when you solve works out to be 3.098 times 10 to the negative 3. And then using our equation that we were given earlier, pH equals negative log of H3O plus, or H plus. I'm just going to write it over here now. pH is negative log, let's say, of H plus, which equals negative log of 3.098 times 10 to the negative 3, which works out to be 2.51. So our answer is C. Okay, so the next section is 3.4, which looks at buffer solutions. So the whole idea of a buffer solution is that it resists the change in pH of the solution when a small amount of strong acid or strong base is added. And for this to happen, there are a few requirements, which it must have a weak acid and a weak base that will not react with OH minus or H3O plus ions, respectively. And they also cannot react with each other. So the only way for this to actually happen is to have a weak acid or base and its conjugate pair. Typically, they're in a 1-to-1 ratio, and they must be in large quantities. So this ties back into our weak acid and base topics, talking about the common ions effect, as the conjugate pair acts as a common ion with either the weak acid or base, both existing in equilibrium. So there's a couple different ways you can prepare a buffer solution. I'll talk about the acidic buffer preparation, but all the same concepts apply, just flipped for basic buffers. So the most basic way to make a buffer is just to combine large and relatively equal quantities of the weak acid and its conjugate base into water. The other two ways you can make a buffer are by starting with one of the two components and adding the strong acid or strong base to create the second component. So for this, you want to convert about half of the species you're adding into its conjugate base so that it exists at equilibrium. So knowing how to calculate the pH of a buffer is really important, as the pH is the main purpose of a buffer solution, right? So there's two different ways you can figure out the pH of a buffer. The first being using the molarities or moles and setting up an ice table, which we covered last section. There's a couple things to remember: that if the parent species and its conjugate base must be in units of molarity, as well as that diluting the buffer has no effect on the pH. The other way to calculate pH is using the Henderson-Hasselbalch equation, which is shown here. Where the numerator is the conjugate base and the denominator is the weak acid. Either work. It just depends on what information you're given. For example, if you're given K over pK, you might choose to use the ice table instead. But again, just keeping in mind the relationships that I've listed on previous screens. Okay, so finally, we'll talk about titration curves. So acid-base titration curves are super useful and used all the time in chemistry when you need to find the equivalence point, which lets you determine the strengths or what kind of indicator you can use. One key term I want to cover real quick is the equivalence point, which is when stoichiometrically equivalent amounts of the acid and base have been combined. So the equivalence point doesn't always mean that the solution is neutral or has a pH 7. It can be acidic or basic, just depending on the strengths of the species combined. So our example here, with a strong acid and a strong base, the pH will always be 7. But if you have a strong acid and a weak base, you're not going to have a neutral equivalence point. Since we have a strong acid, we're going to have an acidic equivalence point, and the opposite here. Since we have a strong base, we're going to have a basic equivalence point. So once you have a strong and a weak species combined, there's a region on the curve called the buffer region, which is where the solution's actually acting like a buffer, since the conjugate pair is being formed. And you can actually see on the curve how this is buffering, as there's a very small change in pH when a large amount of either acid or base is added. So then once either enough acid or base is added, the solution can no longer buffer, and we start to reach the equivalence point. Just before that, though, we do have what's called the midpoint. So half the volume needed to reach the equivalence point is where the pH is equal to the pKa. So for example, if this is 10 milliliters to reach the equivalence point, at 5 milliliters added, the pH will equal the pKa. Then we come to the actual equivalence point, which is the point of inflection of the curve. Here, the pH changes dramatically when just a small amount of acid or base is added. You can see the drastic change in pH. Eventually, it will plateau out, and you have either excess titrant of acid or base added. Okay, so here are just a couple practice questions. Again, go ahead and pause the video now to try it first. Sorry, I forgot to give the pKa in the question here, which is 4.752. Okay, sorry about that. So since we're given the pKa, it'll be easier to use the Henderson-Hasselbalch equation, where pH equals pKa plus log of our conjugate base over our acid. And here we can just plug the values in. So 4.752 plus log of 1.0 molar over 0.8 molar. And then when you solve, you get 4.752 plus log, plus 0.097, which equals 4.85. When we round, we can see our answer here is D. And our final question isn't a multiple choice, but it's a good, it's good to go through and be able to identify all these points by yourself. So again, go ahead and pause the video here. Okay, so for this first one here, we can see our pH at our point of inflection is 7. So it's pretty obvious we have a strong base and a strong acid. Which is also seen by how acidic it starts at. We have a very low pH and it ends very basically as well. So that's kind of another indication. Whereas for this example here, we're starting much closer to neutral. Still acidic, so very likely we have a weak acid here. We have our buffering region here. We have our buffering region here. And we have our point of inflection about here. So we can see that it's becoming more basic. So we are titrating with a strong base. So volume of base added. And here you can see it plateaus out very basically, right? We're getting very close to 14 for the pH. And then finally here, we have a slightly basic start. We're not as drastic as where we finished this previous example. So we have a weak base. We have our buffering region here where we're adding lots of volume and we're getting little change in pH. And then we come up to our equivalence point where there's a drastic change in the pH with little change in the volume. The equivalence point is acidic. So we know we have a strong acid as our titrant. The volume of acid added.
Hey guys, my name is Reina, and I will be your academic mentor for the last chapter, Chapter 4, Electrochemistry. So for this chapter, there are a lot of content, and instead of teaching you guys everything, I would briefly go over what you need to know, explain some common confusions, and show you how to apply the knowledge using some practice problems. You should first understand the mechanism, then try your best to memorize and familiarize them by doing practice problems. 4.1 Redox Reactions. So first, you need to identify a redox reaction. So if there are changes in the oxidation states, then it is a redox reaction. I know some people may say if there's elemental substances in the reaction, then it's a redox reaction. But while you can say that, however, not all redox reactions contain elemental substances. So for example, for this reaction, just by looking at it, you may naively think that it is not a redox reaction. But if you write down the oxidation states, we can start from oxygen. So all the oxygens are -2 here. So this is plus 8/3, plus 2 for carbon, plus 2 for this iron, and plus 4 for this carbon. So we can see that the oxidation states of iron and carbon changed. So keep in mind that there are special cases, and you should always look at the oxidation states. Okay, next, you need to know how to separate the overall redox reaction into two half reactions. So one thing I want to clarify here is if something is being oxidized, it is a reducing agent because it helps the other reactant to undergo reduction. So you can use acronyms like Leo-Szilard or OIRIG. I personally prefer Leo-Szilard because it tells you to look at electrons specifically, but you can choose whichever you want. Okay, and you should know how to assign the oxidation states. And usually we start from carbon, so it's +4. I know here we have a +2 carbon, but this is an oddity, and for most first-year exams, you can just use +4 for carbon. And then for oxygen, we have -2, +1 for hydrogen. Halogens like fluorine, bromine have -1. And for group 1 and group 2 metals, for group 1 it is +1, and for group 2 metals, they're +2. And for all elemental substances, all of their oxidation states are 0. And lastly, you should know how to balance various types of redox reactions. One thing I want to emphasize here is not to balance just based on the atoms, but instead based on the number of electrons. So you should make sure that the total number of electrons lost is equal to the total number of electrons gained. Okay, so here we have a redox reaction. And I'm going to show you how to separate this redox reaction into two half reactions. So first, we assign their oxidation states. For elemental zinc, it's 0, and this ion is +2 for copper ion, and +2 for zinc ion. For the solid copper, it's also 0. So for zinc, the oxidation state is increased by 2. So we write an arrow because it's increasing, and we write 2 here. And for copper, it decreased by 2. So we write another arrow here, and we also write 2. So now we connect the arrows, and we see both 2 here. So we can just write ×1 ×1. So 2 electrons are being migrated from zinc to copper. And I already told you guys about Leo and Gerd. So because zinc is losing electrons, so we write the half reaction for zinc, which is oxidation, and then we can write the half reaction for copper, which is a reduction. And don't forget to write the electrons here. One way to not forget about electrons is to keep in mind that the two sides of the arrow should have equal charges. So on this side, this charge is 0 and this charge is 2. That means we have to have 2 electrons because each electron has -1 charge. And same for reduction. Next, we're going to talk about voltaic cells. So voltaic cells are also called electrochemical cells or galvanic cells. They're different from electrolytic cells, and one way to memorize the difference is by looking at the word electrolysis. So if you're in bio, you should know that the suffix lysis means to break down something. So for electrolysis, It is breaking down the electrical energy, aka electron, to force a reaction to happen. For voltaic, it literally means to generate current. So here we're looking at voltaic cells, so the reaction should be spontaneous and it is generating energy. So now let's look at this voltaic cell here. So on the left-hand side, we have an oxidation reaction, as I just explained in the last slide. And the electrons lost by zinc travel through this wire all the way to the beaker on the right side. In this beaker, we have a reduction reaction utilizing the electrons just landed here. Keep in mind that oxidations always happen on the anode and reduction always happen on the cathode. One way to memorize this is to look at the first letter of each word. So A and O are both vowels, and C and R are both consonants. So if the reaction keeps going, eventually there won't be any electrons left in the zinc beaker because they're all in the copper beaker. So to compensate for the negative charge loss in the zinc beaker, we connect the two beakers by a salt bridge, which is just an inverted U-tube. Glass wool is added to the two ends of the tube so the potassium sulfate doesn't mix with the reactants. And by that, this voltaic cell can keep going and generating energy for this light bulb here. Then you should be able to write out the cell diagram from this voltaic cell. We start from the anode and we write in the same order as we write the half reactions. We should always write down the phase of a substance, and if there's multiple substances in the same phase, we just divide them by a comma. So like for example, if we have both A and B in solid state, then we just write A solid, comma, B solid, and then keep going. So between different phases, we use a single vertical bar. So here we start from the anode and we write this solid zinc first, and then we write the product. Zinc ion is in the aqueous solution, so we write AQ. They're in different phases, so we write this single vertical bar. Note that we don't need to write down the electrons. Then we write the salt bridge, which is a double vertical bar, and now we do the same with the cathode. Now that we have a current generating cell, we're interested in the cell potential or cell voltage. For cell potential, it is the electrical energy difference between any two electrodes in a voltaic cell. It depends on the nature of reactants, concentrations, pressures, and temperature. We use a voltmeter to measure this potential. However, only the potential difference for a whole cell can be measured. So if we're interested in the potential of a half cell, we need to use a reference, which is called the standard electrode potential. For the standard electrode potential, this value would be given to you either directly written in the question or in a table. The standard electrode potential is the tendency for a reduction process to occur at an electrode. So in a table like this, you should only see E0 reduction values. As I said before, oxidizing agents are reduced. So the stronger their oxidizing ability is, the easier for them to be reduced, therefore a more positive E0 reduction value. For a standard cell potential problem, you need to first identify the two half reactions, and you need to know which one reactant is being reduced and which one is being oxidized. If you're not sure, just compare the E0 reduction values to see which reactant is easier to be reduced. So for the oxidation half reaction, remember to take the value with opposite sign, because instead of gaining electrons, it is losing electrons. That's why you should take the additive inverse of the original number. Lastly, add up the E0 for both half reactions to get the standard potential for the whole cell. Note that this little circle naught stands for standard condition for electrochemical cells, which is 1 molar concentration and 25 degrees Celsius. Therefore, in this case, we don't need to multiply the concentration of reactants because it is already implied in the standard condition. Now we have the standard cell potential. We can use this formula to evaluate the standard free energy. Delta G0 equals to minus NFE0 cell. N is the number of electrons in moles, and F is the Faraday constant. From the previous chapter, we can know that when E0 cell is positive, the reaction is spontaneous. If it is negative, the reaction is non-spontaneous, and its reverse is spontaneous. And if the standard cell potential is 0, then the reaction reaches equilibrium. If it's not a standard condition for the voltaic cell, either because of the temperature or the concentrations. We use the Nernst equation to determine the cell potential. Recall that Q here is the reaction quotient, which you should already know from previous chapters. Okay, so now we have a practice problem. Determine E0 cell for the given cell diagram. Is the reaction spontaneous? Calculate the cell potential of this cell at 25 degrees Celsius and concentration of zinc ion is 0.50 mole per liter and concentration of copper ion is 0.05 mole per liter. Okay, so for this cell diagram, we can write out the anode side, and for the cathode side, we can write a similar reaction. And these two E0 numbers are from the table. Note that we take the opposite sign for the oxidation part. So if we add up the two numbers together, we would get the E0 cell, which is positive 1.10 V. It's bigger than 0, that's why delta G0 is smaller than 0, so the reaction is spontaneous. For the second part, we use the Nernst equation. So now we need to know what N is and what the reaction quotient is. So we write out the full reaction. So now we get Q is equal to 10. And lastly, we plug in the numbers and get 1.07 B. Okay, so next question. Consider the following cell. The standard cell potential for this cell is 1.26 V. When an electrochemical cell using these reagents was prepared in a lab, the measured cell voltage was only 1.17 V. What is a possible explanation for the observed voltage? So we already know that it has nothing to do with surface area, so we cross out A and C. And for B, we only talked about the volume. However, the concentrations are not mentioned, so we also cross out B. And we're only left with D and E. So from what I explained earlier, the measured cell voltage would be different if the concentration is different or the temperature is different. So we use Nernst equation. And now we plug in the numbers from the question. So now we know that for this part, it is positive 0.09 B. We know that for this part, it's always positive, so it would make this long Q a negative number. So in a graph of ln x, it is continuous and increasing on its domain. When x is equal to 1, ln x is equal to 0. So for ln Q to be negative, Q is less than 1 and bigger than 0. And we can write out the Q from this cell diagram. So in theory, Q should be equal to 1. However, if there's more aluminum ion or less cadmium ion, then Q can be less than 1. Therefore, we choose E. Now let's talk about electrolysis and electrolytic cells. Electrolysis is the process when a non-spontaneous chemical reaction is forced to occur using electrical energy. So for an electrolytic cell, it is very similar to a voltaic cell, but in this case, since we use power to force a non-spontaneous reaction, the spontaneous reaction is reversed. Oxidation still happens at the anode, and reduction still happens at the cathode. So in this case, electrons are migrating from the copper beaker to the zinc beaker, and we can say it is in the recharging mode for this Daniell cell. So sometimes if the products of two half reactions don't react with each other, this cell can be simplified. So instead of putting the two electrodes in separate beakers, we can put both of them in one vessel filled with an electrolyte solution. For a non-spontaneous reaction, delta G is positive, so E0 cell is negative. Therefore, the minimum standard voltage you need to force this non-spontaneous reaction to occur is minus E0 cell. Since this is the minimum, when there is more voltage applied, the additional amount is called the overpotential. In real life, overpotential is inevitable, and it means higher consumption of electrical energy and higher production costs. Now we have a very important example here, which is the electrolysis of water. In this case, we have a simplified electrolytic cell. Electrolysis of water is a redox reaction, and when we're dealing with neutral water, the water is reduced and oxidized at the same time. So for reduction, two waters gain 2 electrons and are reduced into 1 hydrogen gas and 2 hydroxides. For oxidation, 2 waters lose 4 electrons and are oxidized into 1 oxygen gas and 4 protons. If there is an acid or base in the solution, the voltage will be different because protons interfere with the redox behavior of water. In an acidic condition, since there are more protons, the protons undergo reduction, therefore the half reaction would look like this, and the oxidation part does not change. Likewise, in a basic condition, there are less protons, so the hydroxides undergo oxidation, and the reduction part stays the same. When the electrolytic cell contains a mixture of compounds, multiple reactions can happen, but normally one of the reactions will be favored. The preference is made based on the ability of reactants to give up or attract electrons. So for both reduction and oxidation have reactions, the more positive or negative their E0 is, the more favorable the reaction. Next, we have Faraday's law, which states the simple quantitative relationship between the amount of electricity passed through the electrolytic cell and the amount of substances produced by the reaction. So Q here is the charge, not the reaction quotient. And E is the moles of electrons. Here the subscript E means electrons. F is the Faraday's constant, I is the current in amperes, and T is time in seconds. So lastly, you need to know the chlor-alkali process, which is just an application of electrolysis. I'm not going to go into details, but you need to know what the reaction is, how it works, and you can use this example to check if you understand the concepts earlier in this chapter. We have another example here. A solution of gold chloride is electrolyzed for 20 minutes using a current of 2.5 amperes. What is the maximum mass of gold that would be deposited at the cathode? In this question, we're dealing with current and electrolysis, so we use Faraday's law. We have time, current, and the Faraday's constant, so now we plug in the numbers, and we get the number of electrons, which is 0.03109 moles. Now that we have a value related to the reaction, we can write out the redox reaction. For each one gold chloride molecule, 3 electrons are involved in this redox process, so there is 0.01036 moles of gold chloride. Lastly, we calculate the mass of gold and get 2.04 grams. So we choose A. Last part, batteries. Batteries are devices that convert the chemical energy stored in its active materials into electrical energy. Batteries are classified into primary and secondary batteries. For primary battery, it is not rechargeable because it involves an irreversible reaction. For secondary batteries, they're rechargeable because the chemical reactions involved can be easily reversed, for example, the ones in your laptop and cell phones. And in this charging mode, a spontaneous redox reaction in a battery supplies an electric current. This spontaneous reaction continues until the battery dies. There are 2 reasons for a battery to die. So the first is when the reaction involved reaches equilibrium, so delta G and E cell are both 0. The second case is when all the reactants are used up. So if this dead battery can be recharged, the original Voltaic cell becomes an electrolytic cell. Therefore, reversible cells are essential to rechargeable batteries. We have some examples for batteries here. And for these batteries, you need to have a general idea of what they are and how they work. You don't need to go into very specific details. However, you can use these examples to practice applying concepts. So we have the lead-acid battery, which is the world's first rechargeable battery. And we also have other rechargeable batteries like nickel-cadmium batteries, nickel metal hydride batteries, lithium-ion batteries, and lastly, lithium polymer batteries. So that's it for the review session, and I wish all of you good luck on your midterm.
Hi, I'm Nicole, and I will be talking about reaction rates. So starting off with section 5.1, reaction rates and rate laws. What is a reaction rate? A reaction rate measures how fast reactants are converted into products. The rate of a reaction depends on the nature of the reactants, the concentration of the reactants, and the temperature at which the reaction proceeds, as well as whether or not there's a catalyst present. So for a reaction, this one here, where A plus B go to form C plus D, the rate law can be written as K, which is the specific rate constant and dependent on temperature, times the concentration of reactant A to the exponent of X, times the concentration of reactant B to the exponent of Y. Both of these exponents are the orders for each reactant and can only be found experimentally, which I'll show on the next slide. Before moving on, though, it's also important to note that the rate is always positive, so it always will give you a positive number. So for determining the order of a reaction using the order for each reactant, if X is equal to 0, the reaction is 0 order with respect to A, and A will have no effect on the overall rate. If X is equal to 1, the reaction is first order with respect to A, and the rate is directly proportional to A. And if X equals 0, the reaction is second order with respect to A, and the rate is quadratic to A. The same thing applies for the exponent Y and reactant B. Overall, the total rate order of a reaction will be equal to X plus Y. So the sum of all orders. So determining the rate law experimentally, or the rate order, experimentally, you can start by determining the rate order with respect to each reactant, which can be done using the method which compares data from multiple trials of a reaction using the ratio formula shown here. You want to make sure that you choose 2 trials in which only one of the reactants are changing. So in this example here, for this reaction, trial 1 has a concentration of reactant A that's equal to 0.1 molar and a rate that's equal to 0.02 molar per second. And trial 2 has a concentration of 0.2 molar and a rate of 0.1 molar per second. If you put these values into the formula here and solve for X, you'll get a answer of 2, which means that the reaction is second order with respect to A. Now moving on to the overall reaction order, there's 3 of them. So there's 0 order reaction, you can have a first order reaction or a second order reaction. This table here sums up all the important key aspects and distinguishing features of each type, including their rate laws, their integrated rate laws, which will give the straight line plot, the slope of the plot, their half-life, and their half-life formula, and the units. Using these, you'll be able to distinguish based off a plot or based off a rate law what kind of reaction order you're dealing with. And these are the straight line integrated rate law plots of each type of reaction, where 0 order and first order reactions will have a negative slope, which will be equal to negative K. 0 order reactions will have a y-intercept of the concentration of reactant A initially, and the y-intercept for first order reactions will be equal to the ln of the initial concentration of reactant A. For first order reactions, they also follow an exponential decay path, which is only dependent on K, and this can be used to calculate the half-life of different types of materials. Lastly, second order reactions have a positive slope of positive K and a y-intercept of 1 over the initial concentration of reactant A. So moving on to reaction mechanisms and the Arrhenius equation, starting off with kinetics and thermodynamics. So both of these concepts are 2 important areas of chemistry, and they explain different aspects of chemical reactions. They both describe how reactions occur, but they focus on different factors. So thermodynamics determines the net energy difference of a reaction and is concerned with energy changes that occur during a chemical reaction. It doesn't tell you how fast the reaction occurs, and it only tells you whether or not a reaction will happen at equilibrium. Whereas kinetics, on the other hand, is concerned with the rate at which a reaction occurs and the pathway that it takes to reach the equilibrium. It focuses on factors such as activation energy, which is the minimum amount of energy required for reactants to overcome this barrier of energy and to go from reactants to products. A higher activation energy will equal a slower reaction, and a lower activation energy barrier will equal a faster reaction. Heat can also be used to provide the necessary energy to increase the fraction of molecules that can overcome this activation energy barrier. But without overcoming this barrier, the reactants will not be able to move over and turn into products. So when talking about chemical kinetics, an important concept is collision theory. This theory explains how chemical reactions occur and why reactions happen at certain rates. It focuses on the idea relating the number of collisions, the probability factor, and the fraction of collisions with enough energy to the rate of the reaction. The number of collisions is important because more molecules will equal more collisions, which will result in a faster reaction rate. So therefore, having a higher concentration of reactants will give you a faster reaction. Now, molecules need to collide in the proper orientation in order for a reaction to actually occur. So not all collisions will result in a reaction. Even if 2 molecules collide that have enough energy, but don't align in the right way, then they won't form products or won't form the correct products. So the probability factor is a steric factor that determines the probability that molecules will collide in the correct orientation to actually form products or form a reaction. And the fraction of collisions with enough energy relates back to the activation energy. So we need enough molecules to collide with enough energy to be able to overcome the activation energy barrier to start the reaction and to convert the reactants into products. The Arrhenius equation. So this is a mathematical formula that describes how the rate constant of a reaction depends on temperature and activation energy. It's a key equation specifically for chemical kinetics, and it helps to explain the temperature effects of a reaction. So it shows that as temperature increases, the rate constant will also increase, which means that the overall reaction rate will increase. This is mainly because molecules will move faster at higher temperatures, which lead to more frequent and more energetic collisions. The Arrhenius equation can also be expressed in a logarithmic form, which is useful for determining the activation energy experimentally. This form specifically is useful when data is collected at different temperatures, because by plotting ln of K versus 1 over the temperature, you get a straight line. And the equation of the line can be given in the y equals mx plus b form, where the slope of the line is equal to negative of the activation energy divided by r, the ideal gas constant, and the slope and the line will have an intercept of ln of a, which can be useful to calculate the activation energy from experimental data. Now, the activation energy of a reaction can be changed by having a catalyst present or not having a catalyst present. So a catalyst is a substance that increases the rate of a chemical reaction without being consumed in the reaction itself. So basically, it helps provide an alternative reaction pathway with a lower activation energy required for the reaction to proceed, which then makes the reaction proceed faster, or in some cases makes some reactions possible to proceed. It's important to know, though, that catalysts do not change the change in enthalpy or the equilibrium constant of the reaction, and they do not reduce the rate of the original reaction because both pathways still exist. The catalytic pathway just has a smaller activation energy barrier. A reaction mechanism is the sequence of steps, which are known as elementary steps, that make up the overall reaction. So an overall reaction can be made up of multiple different elementary steps, which will in turn lead to the final product. Each elementary step has its own activation energy and its own rate constant. An intermediate is a species that is produced in one of the steps and is used up in the next. So it's not present in the overall reaction, it's not present in the products, and it's not present, it wasn't present in the reactants either. Molecularity and reaction mechanisms describe the way that reactions proceed and how they are affected by the nature and number of molecules involved. So this brings us to talking about molecularity, which is the number of reactants that are involved in an elementary step. You can have a unimolecular process, which is where A just turns into B with only one reactant and is a first order reaction, or a bimolecular process where A plus B go to form C with two reactants and is at second order. The overall reaction rate is determined by the rate determining step, or RDS, which will be the slowest step in the entire mechanism. And finally, you can use the rate determining step to derive the rate law and from an entire mechanism. To do this, you'll have to first identify the rate determining step, which will be the slowest step, and the step where the transition state has the highest energy. You can write the rate law for the rate determining step, and the overall rate determining step, or the overall rate law of the equation, will follow the rate law for the rate determining step. You have to make sure that you eliminate intermediates because they're not present in the reactants or the products. You can express intermediates as reactants in the overall reaction equation using equilibrium expressions. And then finally, you can substitute and simplify the rate law. After you've identified the rate determining step, any of the fast steps after this can be ignored because they will not play a role in the overall rate law for the reaction mechanism.